Good morning, good afternoon, good evening, everybody. Welcome to the presentation today. My name is Ryan Siegler. I'm a data scientist here at KX, and I'm joined by Nick Ivory. Nick, if you'd like to say hello.
Hey, everybody. Nick Ivory here.
Awesome, thanks, Nick. And Nick's going to be giving a really interesting presentation on doing some time series analytics with Temporal Similarity Search and Temporal IQ. And if you don't know what those are, no worries. We will explain that all to you very shortly. Now, in the meantime, I will give a couple minutes for people to join, and I'm just going to go through a couple of housekeeping items and get everybody the good information here. Number one, yes, this presentation is being recorded. So after the presentation concludes, you will be able to go view this on LinkedIn as well as on YouTube to review any parts that you want to rewatch or just rewatch the whole thing. And secondly, you will be able to ask all of your questions and put your comments into the comment section. And we highly encourage you to do that. Let us know of any questions. You know, our goal is to be able to answer these questions live for you, and we'll look to answer those at the end of next presentation. And if there's so many questions that we can't get to them all, no worries. We'll answer them in the comments after the presentation concludes. A couple of resources for you moving forward after this presentation is number one, we have something called the KX Academy. And there you can find many different free educational courses on a lot of the different products that we have, including KDB.AI, which is what we're going to be talking about today. And that's a vector database. And there's a great course there built by our developer advocate, Michael Ryboy, that really takes you into the introduction of vector databases, talking about indexing, talking about search metrics and embedding models and all that good stuff, and really building up to even more complex use cases like RAG or multimodal RAG. So definitely check that out. I'll put the link in the comments here if you're interested in learning more and going through that course. It's just a couple hours, and at the end of it, you take a little bit of a quiz, and then you get a certificate that you're able to share with your friends and colleagues out on LinkedIn or wherever. And then lastly, we do have a Slack channel that's available to you. It's free to join. It's really a good resource. It's quite an active community. People asking questions about KDB.AI and the other products as well. We have several different channels that are available to you. So we encourage you to join that to get the conversation started. You can get in contact with myself directly, with Nick, and with our entire developer advocate team there. So we encourage you to do that. That's kx.com/Slack. Again, I will put that in the comments section, and we do encourage you to join there. So with that, I think that covers all my introductory items, Nick. So I'll pass it over to you. Fun stuff.
Very good, very good. Well, just by way of introduction, so my name, again, is Nick Ivory. I've been with KX for 3 years now as a pre-sales engineer, and now more recently, a technical account manager. And so my role is to talk with our existing customers and as well new customers to propose enterprise architectures, deliver demos, create proof of concepts that fit our technology into their enterprise architectures and solve really complex data challenges. And I've been working with time series data and real-time data, vector data, going back 10 years now. So I'm super excited to be joining the conversation and presenting to you today. As Ryan had mentioned, we're going to take questions, so hold on to those for the end and feel free to put those into the chat. I'm going to jump right in here and start with a couple of my own housekeeping via an agenda. So I'm going to cover 4 sort of broad overarching topics here. I'm going to give you an introduction to what our Temporal IQ solution is. Now, this is following on the back of a 1.5 years of really interesting conversations and development that we've had with our KDB.AI product and building out those solutions. So we'll have quite a bit to say about where we've been and where we're going. Then I want to talk about what the architecture of this solution looks like, talk about a more granular feature level discussion. Then we're going to talk about what this means to you, the developers, how you can go and use this technology and use it to sell within your organizations as well. The sorts of challenges that we solve and the sorts of opportunities that we have identified. And then I'm going to walk us through the demo. That's probably why you're here. You're going to see some live code. You're going to see some real-time data, and we're going to talk you through that. So without further ado, many of you are already familiar with KX, but just to level set before we get into the real meat and potatoes here, KX has a nearly 30-year pedigree providing financial services institutions with performant data solutions. We are responsible for the transaction of several trillions, it's trillions with a T, trillions of dollars every single day. And we've made a name for ourselves on the strength of our KDB Plus time series database. You can find KDB in 39 of the top 40 US banks. Now, over the last 2 years, something that's brought a lot of our focus has been disrupting the vector database market with the release of our KDB.AI vector database. This powers generative AI applications such as RAG and hybrid search on top of both unstructured and structured data sets. But today we're here to talk about time series similarity search. This is powered by KX's recent technology solution that we call Temporal IQ. And I'll show you what that looks like here. So Temporal IQ, in a nutshell, is a vector data solution which is used to analyze vast amounts of time series data with both speed and efficiency. And it is used to perform what we call temporal similarity search on top of data that is stored within our KDB Plus database. It is a unique solution in a market that largely we see is failing to address structured data search, especially in hybrid search applications. What it allows you to do is search through your vast amounts of time series data, just like you would, your embedded unstructured data in a more traditional vector data use case, and return k nearest neighbors or those sorts of patterns that most closely resemble a specific behavior in question. And what this does is it drives the development of applications that require next level anomaly detection and pattern matching capabilities. So this Temporal IQ solution, as I said before, it comes on the back of 2 years of KDB.AI vector database development. We've been enabling similarity search applications on top of unstructured data sets. Those are your images, your PDF, your text payloads. This is yet another development that we see. Temporal Similarity Search, what we call TSS. It's a proprietary data search algorithm which searches through all of your time series data sets and creates a result for each record and its constituent vectors. And since time series data is inherently directional and it's quantitative, it is inherently vectorized. What this means is because it's structured data, it does not require indexing, it does not require embedding. So you don't have to embed vectors, unstructured data, into vectors using large language models. The inclusion of large language models is entirely not required. So that data, where does it live? It lives in KDB Plus, which is our time series database. That provides the added benefit of not needing to deduplicate data across your different systems. What this offers is the cheapest and most performant vector data search on the market. So just a quick word here. And I want to draw a distinction that this Temporal IQ capability, this solution operates on both real-time as well as historical data. I'll show you this in the demo in just a moment, but what this provides you with is timely insight into your data without having sort of over-engineered complexity, allowing you to pull together both real-time and historical data together in a single context, as well, with your time series data and your vector data in a single context to provide a single holistic view of all of your data sets across the business. So that's one of the unique differentiators about this Temporal IQ solution. Now, I want to talk about how we use TSS, how it's employed into the different use cases that we see. And it's broadly two tranches of problem solving. That's pattern matching and anomaly detection. And pattern matching, taking financial services as an example, is where we look to understand a signal that we've not necessarily witnessed before so that we may classify it in context and then monitor for that same event at a later date in the future. What that provides us is a first mover advantage. And I'm going to keep coming back to that point many times during this presentation, but that first mover advantage on market opportunities, which allows us to mitigate risk and make smarter market decisions. And then the other sort of class of problems that we're solving are those anomaly detection problems, which are identifying extraneous signals that defy our expectation so that we can understand order performance, remediate data feed issues, and proactively address our customer concerns, right? Now, what does this look like as it's deployed into our enterprise architecture environment? So this Temporal IQ solution integrates pretty neatly into your existing KDB Plus architecture. It ships as a Docker container, which has worker nodes that will execute the underlying search query and federate those requests across workers. This creates a very performant layer, right? Now you interact with this Docker container via a number of different interfaces. You can access it via REST if you're building out a JavaScript front end or building out applications. For our KDB Plus developers, we have Q, something that our K and Q developers would be familiar with, federating those queries, pushing them down directly to the database. And then as well, we use Python. And I'm going to show you one example of using Python in just a second. But the important part is that there's a number of different ways that you'd interact with this. Via those interfaces, you can insert your historical data directly from your file system. Or if you're an existing customer using KDB Plus, you may access this on-disk historical database, what we call an HDB, by mounting it directly to the Docker container. So there's virtually zero barrier to entry for getting started, especially if you're already familiar with using KDB. Now, I'm just going to show one or two more slides and then jump into the demo here. What this translates to for customers and where we think we really shine against the competition. I'll talk about some of these points more, but the main soundbite that I want you to take away from this slide here is that Temporal IQ is the cheapest and most efficient solution for temporal similarity search on both real-time and historical data where it resides in situ. And then this is what it looks like in practice. Being the most performant, we have benchmark studies that support that. We could see that performance of our non-transformed, and what that really means is uncompressed data set, that TSS query time looks flat compared to a brute force comparison of a similarity search. And you can see that as data volumes increase, our non-transformed TSS remains relatively flat. That tends to increase with volume payloads. So at around the 2.5 million row mark over here, you could see that we start to flatten out a bit. Whereas, an uncompressed brute force tends to explode in the time that it takes to execute that query. So we've reached the load-bearing portion of our demo where I'm going to take you through what this looks like and show you some live coding and how you would implement this sort of solution for Temporal IQ. Again, I just want to recap what I said earlier. Feel free to put your questions in the chat. We'll revisit those once we get through the demo, and we'll take some Q&A. So I'm going to switch my screen over here, and you should be able to see my workspace now. So a couple things. The first thing that we want to do here is load our temporal IQ memory space. So I'm just going to look at that. Nothing like a live demo. Just give me 1 second. I'm just going to go restart this here. Let's click that. And just going to stop sharing my screen for 1 moment.
Yeah, and while you're doing that, actually, we had a question come in I can field. So the question was, how do you find similar patterns without embedding that time series data? So I know one of the things about the non-transformed temporal similarity search is the search is happening directly on the time series columns that are going through KDB.AI. So that means there's no need to actually do anything with the data except for send it in as it is. So no need to compress, no need to embed. It's happening, the search is happening directly on those floating point values.
Awesome. I'm just about to pull this back up. I'm just restarting my Docker container because I've had the demo running for a while here. So let me pull that back up. Just give me 1 moment here.
So one of the things while you're pulling that up too, explaining a little bit more about like how temporal similarity search works. So there's really 2 different types that are available. One is the non-transform type, and that's what we're going to be talking about today, where you're doing that search directly on the time series columns. It's really good for fast-moving live data, and you can do it with historical data as well, as we'll see. But the other type is transform temporal similarity search. So that's a little bit different, and we can talk about that some more later on. But transform is where you're actually taking the time series windows and then compressing them. So you're saving memory and increasing search speed with that. And another big difference is you're actually inserting those onto a index. So that's one of the big differences. Non-transform today is no index needed. You're doing search directly on your values. Transform temporal similarity search, you're actually inserting into an index, which will speed up your search, especially for large historical databases. Nick, I don't know if you're ready to.
Yeah, we should be able to jump back into it. I've been giving this demo quite a bit over the last few days, and I had my my Docker instance running. So most importantly, the first thing that we were doing here is pulling in data into our temporal IQ memory space. So what we're going to be looking at is a whole bunch of Tesla market data. Now, there are a number of different clients that we can use to connect to our KDB data tables using Temporal IQ. And so we do that using this Python interface first, and we can query our underlying data table, which is this Tesla trade time series data table. So I just ran this here and pulled that data into memory. You can see what that non-embedded data looks like. We have a timestamp associated with that time series data, as well as our ticker symbol, and then market data information around volume and price. So now what I'm going to show you is we've taken 1 week's worth of market data, and this is, again, Tesla stock data, price and volume data bucketed by second. We're going to insert the first 4 days of data into our database, and then we're going to replay the 5th day so that we mimic that real-time data coming into our database. And so we're going to take that live pricing data, and we're going to use that as our search pattern and search for that pattern against our historical data set as it's coming in real time, and return our nearest neighbor value pairs using that search pattern so that we can highlight the results, which are a specified distance away from our live pattern, and show those k nearest neighbors. So this is what it looks like in real time. There we go. So you can see that time series data as it's coming in. That's pricing information that's updating every second. And then you can see in real time, there is a similarity search classification that is happening, showing our nearest neighbors. So what does this data look like versus a historical context? And that's, again, real-time data. Now, you're going to see something in a second here. With our data in this sort of 3-minute sliding window, we have 180 data points. We're showing the result of that similarity search And we want to understand when we have some real-time events that are different. And now you can see we have this sort of conditional live highlighting. We have this conditional formatting, which creates a flag, which colors this skew red, because we see our price information is rapidly increasing here. And that looks very different from our nearest neighbors within certain bounds. So in real time, we're doing anomaly detection to see when does this similarity search defy our expectations. And that creates a moment in time where we can then go and react to it, respond, and ameliorate some, some events. So I'm going to stop our live data coming in right now. And I'll tell you that since this is a real world example, what happened with our Tesla stock? Well, if I scroll down here, we have a bit of a forensic analysis. On that day, at 12:48 and change, Elon Musk sent out a tweet saying that he was going to take Tesla private. And this was much to the SEC's chagrin. Now, looking at that live data, we saw that the Tesla stock price started to climb at approximately 12:48 and 15 seconds. And that is exactly where our algorithm here, our similarity search, detected that there was some extraneous event occurring. So we flagged that, and then we respond to it. So now I'm going to show you another example here where I'm just going to run this real-time data. And you can see, again, time series information that's coming into this engine. And we're going to see some interesting behavior. Now, another feature of this live demo here is that we've created a window length for this example that's a little bit shorter. So it's only showing a minute worth of time. And now you can see, again, conditionally, we've highlighted some unexpected condition. So you can see we've lost information coming in on our pricing feed. What actually is happening here, and you can scroll down and see the nearest neighbors again that are doing that real-time similarity search on our historical data and saying, we have not seen this behavior before contextually. This is an event of interest. So if we scroll down, we can actually see the explanation of that. I'm going to interrupt here. You can see the explanation of that was NASDAQ halting trading for the day. So between 2:08 and 3:45, there was no new pricing information coming in. So you could see that feed shuts off, and our nearest neighbor, search does not find behavior similar enough to that to classify. So a couple of things that are sort of interesting just from looking at this. We can narrow our focus and expand our focus based on how much data and the event of interest that we want to look at. And we can do that by defining a window of a certain length to run that similarity search and look for specific information. And as those live updates happen, you can see the exact moment that trading halted, and immediately our similarity search detects that anomaly and flags the behavior. So one more example here, and this is kind of an interesting one. I'll play our data back here. Now, we're looking at an even more complex example that is showing a multivariate analysis. Let me scroll down a little bit more so you get the full screen here. We're now looking at both price and volume on the same axes, conditioning for that anomalous behavior of price moving against volume. In simple terms, what if we wanted to look for anomalies where our price does not match an unexpected amount of volume? So again, we sort of flag conditionally to see that, we sold off a bunch of volume right up until this moment, and the corresponding stock price and how it moves against it. And viewing those two pieces of information together creates context from our historical data with our real-time data updating on a single chart. So you could see, again, when NASDAQ halts, volume shoots down, we immediately flag for anomalous market conditions. Now, this continuous monitoring of market conditions allows us to proactively diagnose and address issues across our network of data feeds. So you're not only addressing order performance issues, you're given the opportunity to respond and react to customers, essentially offer some amount of customer confidence responding to events in real time. This also provides major market opportunities for surveillance, identifying bad actors, across your different data feeds, looking at algorithm execution, monitoring for market abuse and toxic order flow. And as you detect these changes, you can promote them back in and create a moment to respond and react to market opportunities to offer some amount of competitive advantage. So let me interrupt here and go on to another example. So to this point, what we've been talking about is anomaly detection. I want to talk about the other tranche of problems that we solve, which is pattern matching in particular. Anomaly detection, in the way I'd like to describe it, is focusing on the unknown knowns of anomalous behavior. And what that means is we're monitoring for fault conditions that we expect will happen at some point so that we can respond and react appropriately at an unanticipated moment in the future. And the difference between this and pattern matching. So pattern matching is focusing on the known unknowns. Given some ambiguous market event, we want to be able to search through the history of our data and determine market sentiment based off of events which have occurred historically. So I'm going to show you this example here, and you're going to see, when I run this, you're going to see an M-shaped curve that looks like this specific pattern, right? This is a pretty rudimentary signal. I'll say a bit more about this in a second, but we want to understand this signal and where it's represented in our historical and our real-time data so that when we see it reflected in our live data, we can capture and understand this pricing signal. So we're searching against our live pricing data for nearest neighbors to understand market behavior both before and after some event occurs. And then we do this nearest neighbor classification, like you saw before, to understand where we've seen this in the past so that we can anticipate prices that are likely to follow and offer smarter order execution insight. Now, I would anticipate one objection to this example being, this is a pretty rudimentary pattern, as I mentioned before. You see this M shape reflected all over the place if you're looking for it. It's kind of like looking at tea leaves in a sense. The real world is far more complex. And that's why we have the ability to promote many of these different patterns at once and have sort of granular micro trend signals to both, again, look at sort of smaller windows of time as well as more protracted windows of time, which, if you're passing multiple search patterns at once, becomes a very resource intensive operation. And because of the KDB, the performant nature of the KDB database, it's a very simple operation on top of all of our data because KDB is optimized for massive volumes of both real-time and historical data. So we leverage both the query speed and performance of KDB for this massive columnar in-memory data search and present a solution that is uniquely fitted for the challenge. So let me interrupt this here. And just before we jump into questions here, you can see this is the end of our presentation here. To clean this up, we would manage our session, and you can see the tables that exist here, and then clean up our workspace. So we're interacting directly with the Docker container here, and you can see now that we've deleted that table, there's nothing that exists here. So this is us interacting with the Docker container. I just want to drive home a couple of the points that you've seen today here before we move into the Q&A portion of the evening. So first and foremost, we've been talking about KX's Temporal IQ solution, talking about TSS, which is a proprietary pattern matching algorithm, which allows you the ability to capitalize on trading opportunities, optimize your trading strategies, and effectively mitigate risk. And because this time series data does not require embedding, we can search for curves of variable length, both smaller windows as well as more complex, sort of myopic views of our data, and also look for several at the same time to model more complex market conditions. And this is all driven and powered by the speed and performance of KDB+. The last thing that I'll say is that this solution is available now, this Temporal IQ. So you can reach out to us directly. You can follow us on LinkedIn and reach out there, or you can go on code.kdb.com, excuse me, and find some more information there. Ryan, I think you had some additional links that we can send out. And while we're taking questions, we'll throw those in the chat. But let me pause here. And Ryan, do we have any questions coming through to us?
Yeah. Thanks, Nick, for the presentation. Really awesome stuff. And we do indeed have a few questions from the chat here. Now, this one was one that I partially answered, but there's a bit more to it. So how do you find similar patterns without embedding the time series data? And like I mentioned, that's sort of one of the key features of non-transformed temporal similarity search, is being able to do your pattern matching directly on those time series columns. But how are we doing pattern matching when different patterns might be completely different prices? And one of the reasons you can do that is because you're not just pattern matching, or you are not pattern matching directly on the actual numbers themselves. You're pattern matching on the shape of the signal. So that's why you're able to compare, different patterns that might represent different prices or different values. And can you do the search upon like different types of columns, open, low, closed columns, for example? And the answer is yeah, you can, as long as, in this case, they're floating point values, they're time series values, just like the price. You could do this on your open or closed or low column, whatever column you want. For example, here we looked at price as well as volume. So yes, you can. All right, another question that came in here is someone had a question about the demo, specifically around finding the similar patterns that's in many cases seem to be like directly around the query in this case. So, if you have a query at time 10 minutes and then it's finding similar patterns at 9 minutes and 59 seconds, why does that, can we explain that basically?
Yeah, that's demo magic. And I mean, in the sense that we have so much historical data stored down, but for the sort of time in this demo, we wanted to know these events actually firing off in real time. So what a more realistic real world scenario would look like is having potentially years of market data stored down that is your corpus of historical data that you would then search again with real time data that's coming into this engine. So you've correctly identified, like, yeah, this is just to exhibit the behavior in a real live demo.
Yeah, and one other thing I'll mention about that too is, like, in this case, in this demo, right, you had this set of live data that's coming in, and you're doing pattern matching over that. So of course, like, the similar patterns are going to be right around where the query vector is, but there could also be similar patterns in the historical data. And one way you can handle this, potentially, is creating a filter that basically says, discount any patterns that are right around that query pattern, within, a minute or whatever, and then it would basically force your pattern match to be happening across your historical data as well. So that's one of the other big benefits of using this within a vector database like KDB.AI, is you have all this metadata filtering capability where you can kind of sculpt your query however you want to. And that's really a powerful way to do your searches. So that would be something really cool to add onto this demo. So thanks for the question on that.
Love the engagement.
Sorry, go ahead, Nick.
No, just love the engagement so far. Keep the questions coming.
Yeah, keep them coming. Absolutely. And yep, this will be available on YouTube and LinkedIn right when we finish the presentation. One question for you, Nick. Is Temporal IQ, is that basically just for time series data, or is that for unstructured data as well?
Great question. So Temporal IQ is a time series specific solution. And this was developed because of a lot of the attention that we've been getting around KDB.AI. We've had KDB customers coming to us saying, well, we'd love to be able to do TSS on our structured market data, structured time series data on top of KDB directly. So that's where Temporal IQ came from. But for the unstructured side of the house, where we're talking about, text data, PDF data, image data, video data, et cetera, we use KDB.AI. And so these are the sorts of conversations that we've been having for about 2 years now, talking through vector data use cases that do require embedding and chunking and tokenization of unstructured data sets. So we've been building out these applications. We have a lot of demos that we can show specifically around that regard. And if there's something you're interested in seeing, feel free again to reach out directly to us to see a demo, and we can set that up and show some of the solutions we've been putting together.
Awesome. And one other question, questioning where's this data actually coming from for this demo? And I believe that's from KDB plus database in this case.
Exactly. Yeah, it's market data that's stored down in KDB.
Right. So this is coming from a KDB plus database, and this is like one side of the coin for Temporal IQ. And then on the other side of the coin, you can also do temporal similarity search in KDB.AI, without needing to be using KDB plus at all too. So really either way, whether you have your time series data stored in KDB plus, or you just have time series data and you want to run TSS directly with KDB.AI, you can do this, whatever way you want to. All right,
Yeah.
Let's see if any other questions have come in. So one question about Milvis. So is our product more suitable in many cases for the financial services vertical and working with time series data? And I'll, Tristan, thank you for the question. Really appreciate the question. I think it's an important question. Nick, if you want to take this, or I can, either way.
Well, I'll take it. I'll run with it, and then I'd be curious to hear your thoughts as well. I think any answer would have to fairly live in the realm of opinion, but I think one indisputable fact is performance. And as far as the interaction between your vector database and your massive amounts of data that's stored down on your file system, wherever it resides, you can't argue with results. Like KDB Plus has a super performant in-memory compute engine that has been, road tested for 30 years in the most rigorous, robust market data and real world use cases for post-trade, pre-trade, high frequency trading, and that is what backstops this Temporal IQ solution. I think Milvis has been doing some really interesting things. I'm trying to remember what their managed service offering is, but they're not necessarily suited for time series data applications. And Ryan, I'd be curious to hear as well, your thoughts on it, because we certainly hear quite a bit about Milvis in the market.
Yeah, sure. Yeah, it's Milvis. There's plenty of other vector databases out there, but with KDB.AI, you have your basic vector capabilities, hybrid search, multimodal search, all that, multiple index search now, which is one of the new features that we're super excited about. But yeah, when it comes down to like the time series side of things, that's where you're going to see a big differentiation. And yeah, whether it's for financial services, of course, that's a big one, especially with the history of KX and KDB plus. But really anywhere you're working with time series data, especially fast moving time series data, for example, like manufacturing or IoT environments, like those types of environments would be a good fit for this as well. So pattern matching, time series analytics, I think that's one of the big differentiators, and definitely recommend you try it out. We have many demos up on GitHub right now. You can open them up right in Colab, get started within a couple minutes. So definitely recommend you check all that out. All right, so if you want to try KDB.AI, this is another good question. Let's see here. So if you want to try KDB.AI, you can just go to KDB.AI, and there what you'll be able to do is sign up, and you'll get your API key and endpoint. It's really easy to do. It takes a couple minutes to sign up. And then once you do that, you'll be able to literally open a Colab notebook, which we have a bunch of them available for you. And you could get started with a multimodal RAG use case from scratch within 5 minutes or less. And then if you want to do, and there's a bunch of temporal similarity searches as well. So plenty of options for you to try all this stuff out, whether you're looking more for the unstructured side of things with more traditional vector searching, or you want to try out some of the time series similarity search stuff. It's all there for you, and it's really easy to sign up, KDB.AI. Okay, so there's a few more questions, but I think we're coming up on time here around the 45-minute mark. So what I want to do is close out the presentation, and then I will be getting back to any of these questions in the comments after the presentation. We definitely want to get these questions answered for you. So with that, Nick, unless you had anything else you wanted to add.
No, I'm all good on my end. I want to thank everybody for joining and taking the time today. We'll be posting this online again, and please reach out if you have any further questions and you want to see a demo.
All right. Thanks, Nick, and thanks everyone for joining. Awesome. Again, check us out on the Slack channel, kx.com/Slack, and really appreciate your time. We know it's important to us that you're here, and we appreciate that you take the time to be here with us. And looking forward to talking further. Thank you all.